Hello, AP Chem students, and welcome to topic 6.8, Enthalpy of Formation. So the learning objective for today is 6.8.a, calculate the enthalpy change for a chemical or physical process based on the standard enthalpies of formation. So again, we're continuing with this idea of how we calculate the enthalpy of a reaction. So we've looked at if the enthalpy is given to you at the end of the reaction, how we manipulate that. In our last video, we looked at bond enthalpies, and so now we're going to look at standard enthalpy of formation. So standard enthalpy of formation can be used to calculate the delta H value for the overall reaction. So again, just another way to calculate that delta H. The standard enthalpy of formation is the change in enthalpy required to form a substance relative to its reference state. So the reference state is the state in which an element exists at 1 atm and 25 degrees Celsius. So again, the element. How does the element exist? So know this, that the standard enthalpy formation of a pure element in its reference form is 0. And so we have set that to be the case, and then everything else in terms of enthalpy of formation is relative to those values. So here we go. So if we look here, we have the formation of water, and we have elemental hydrogen. Remember that hydrogen is a diatomic, and then here is half of elemental oxygen. So both of these values are going to be 0. And so then you can calculate the delta HF standard. You can measure the delta HF standard relative to those values. And so these numbers will be given to you in the form of a table or in the prompt itself, right? But again, really important to remember, elements in their elemental form are 0, okay? So when you calculate delta H, again, they'll be provided to you in the question or in the form of a table. And note that the values are state dependent. So back to that idea of elements in their elemental form are 0, if you have them in a form in which they are not normally found under those conditions, then that would not be 0. So for example, if you're looking at something like, I don't know, liquid oxygen, which is pretty unusual, but if that happened, then it would not be a value of 0. But again, those liquid oxygen would not be at standard conditions anyway. So using the equation, delta HF is equal to the sum of your delta HF standard of your products minus your delta HF standard of reactants. So again, in this unit, pretty much all the time, unless we're thinking about bond enthalpy, it's going to be products minus reactants as it is here. So this can help us find the delta H standard of an equation. So the easiest way to think about this is just to do a practice. So we're going to do a practice. So calculate the energy released by the combustion of ethane using the information in the table below. So here's your table. And then if you want to go ahead and try this on your own, that would be great. Go ahead and pause the video because I'm about to go through the answer. So we need to first know about combustion. So remember that combustion is where complete combustion, which is what we're going to be considering. It's where you have your hydrocarbon. So here's C2H6, and it reacts with oxygen to form carbon dioxide and water. And then, of course, it's very important to balance that equation. So here is your combustion equation, and then you need to balance it. So that's what that would look like when it's all said and done. So now we can think about our equation for calculating the delta HF. So we're going to do products minus reactants. We're going to use the values over here, and we need to take into account the coefficients. So we can substitute. So we're going to do 4 times your value for CO2, 6 times your value for water. We're going to sum those. And we're going to subtract the sum of 2 times your ethane plus 7 times your O2. Now, you might already recognize that O2 is an element in its elemental form. So this value over here is, of course, going to be 0. But we can plug in the other values from the table. So a lot of times I have students forget that elements in their elemental form are 0, and they will say that number wasn't provided in the table. That is correct, because it is expected that you understand that elements in their elemental form are 0. So don't forget that. All right, so we're going to plug in your CO2 here, and that's going to be your negative 393.5. Water, I gave you both gas and liquid, so it, again, is important to pay attention to the state. So the gas here will be negative 241.8. minus 2 times negative 84.7 for your ethane, also in your gaseous form, and then 0 for oxygen. And then once again, we're going to let our calculator do the heavy lifting here. We're going to get negative 3025.8 minus, so that's the sum here, minus the sum over here, which was negative 169.4. And you get an overall delta H of negative 2855 kilojoules. And so you do want to stop and think, does that make sense? And the answer is, well, yes, it does, because this is combustion. And so that is quite a lot of energy compared to what we see from a lot of reactions, but we would expect that for combustion. Combustion is strongly exothermic. So what should I be able to do with this? Well, you should be able to calculate the delta H for a system using provided enthalpies of formation using the equation, which again is on the equation sheet, and that is it. So I will see you once again very soon to look at yet another way to calculate enthalpy of a reaction.